Bing.
Hi, I'm Vernooy. My project was a Bluetooth oscilloscope, and my advisor is Dr. Wazir for this project. So this was the original design at the beginning of Senior Design 1. You can see it's a microcontroller that's controlling, that has its own digital analog converters. So the input signal goes through B and C connectors, and there's a preamp to get it into the right area for the analog to digital conversion, and that's being sent over UART to the Bluetooth module. There's status LEDs to show when the Bluetooth is connected, and then there's a battery and a battery controller. This was the ultimate goal of having a PCB that was just something small and simple. And this shows what the case would be like. It would be flipped, the board would be flipped upside down, and there would be a battery underneath, so that it would have low center of gravity and wouldn't tip over so easily. And that's just a 3D render of the case itself. So this is closer to what it currently is. This is a simplified design of it. This is the board. It's an ARM Cortex M4. And this is the amplification circuit. That's the Bluetooth module that's connected over UART. And these are substituting as DNC connectors right now. So the microcontroller is Cortex M4. It's a 32-bit processor with an FP unit, and it runs at 80 megahertz. There's two 12-bit analog to digital converters that run at 1 megasample per second. It's got 8 UART ports, 2 I2C, and 4 SBI. There's 2 buttons that's controlled by the user and a restart button on there. And it connects to boards that are produced by TI. And it's flashable over USB rather than JTAG. So there's these are the available sample rates. The best outcome would be to use the top here and then down, as that will be the most accurate using hardware over sampling. And those are the only options for the onboard analog to digital converter. And this is the Bluetooth module that I'm using. It's for an Arduino board. It's by Cduino, and it's Bluetooth 2.0, and it has a serial port profile, which allows me to send UART over Bluetooth. And those are the available baud rates. So this is demonstrating the initialization. It doesn't use AT commands like some other Bluetooth modules. I had to add a delay after each character and after each group of characters in order for it to initialize correctly. So this is the amplification circuit. There's a BNC connector on this end, which is connected to ground, and then there's a voltage divider that's being amplified by a programmable gain amplifier, and then it goes, well, this is a programmable gain amplifier, and this is the amplifier just to make sure that it's within the 3.3 volt range, and then that signal is sent to the analog to digital converter. So the specifications of the amplification circuit, these are the 2 modules that I'm using. The first is MCP626. It's SPI programmable gain amplifier, and there's 8 discrete options for the gain. There's also 6 channels of input which are multiplexed, so that you can ultimately get more gains out of the module, and it has a bandwidth from 2 to 12 megahertz and low error. The other is just a quad op amp with high bandwidth. So for getting more gain as a programmable gain amplifier, I'm using a voltage divider here to reduce the signal from like 75% of what it would normally be. So from 2 channels, instead of just having 8 options for gain, we have 16 options for gain. And that's just a simple voltage divider. So here's a serial communication with a programmable gain amplifier. Clock starts on a low signal, and we have 16 bits. The first 8 are for the instruction, and the last 8 is for the data. The instruction that this accepts is 4.0 and 4.1 in hex. The first is to change the gain, and the first is to set the channel, and the second is to set the gain. And here we can see the pinout of the connection. So this is how data is sent over Bluetooth right now. First going through the loop, it's got a 12-bit sample from the analog to digital converter, and that sample is converted down to 8 bits. And then if it's an 8-bit, if that's a 255, if the character is 255, then it's converted to 254 because I'm using 255 as a termination of the end of the packet of information. And then that's sent over my Bluetooth connection. This cycle goes through 1,000 times, and that's the full packet that's terminated with the 255. So packets are received through an interrupt from the UART connection. This is the 8-bit character. The first 2 sets the channel, and right now the second 2 bits here are unused, and the last are for the gain. For setting the channel, I mask these off, and then I shift them 6 places over, and then that's used for 0 through 3 to show if both channels are on, or no channels, or 1 or 2. And then the gain index is all 16 gains from 2 channels. So the software is split into 2 parts, the microcontroller and the client. As I'm using Texas Instruments ARM processor, I'm using Code Composer. It's based on Eclipse, which is an open source IDE. And it retails for about $800, but you can use it for free if you buy one of the launch pads from Texas Instruments. This is the main function. First, I initialize the microcontroller, all the hardware, and then I set the name of the Bluetooth and make sure that's inquirable. And then I delay for 70 seconds so that a computer can sync with the Bluetooth module. And then I enter the loop as I showed in the other flowchart. And in this loop, I have blinking red and green, red and blue, to show either the red channel, the first channel, or blue, the second channel, is currently on. And then it increments the counter and goes through like before. So these are the clients that would ultimately be used. MATLAB would be a good client for the computer. And then you are sent over Bluetooth, would be able to connect to Android and iOS devices. So in this project, I had some setbacks. I initially wanted to make my own programmable gain amplifier using an R2R ladder and switches. Since there's so many GPIO ports on the microcontroller board, I wanted to do it that way. But I was having issues and it was just taking too much time. It would probably be cheaper that way, but it's not something that I had time to do. So another issue that I had was that the analog to digital converter on the microcontroller was only 3.3 volts at a max voltage. So I had to make sure that my amplification circuit had it had to be very accurate because a small change would make a big difference for the 12-bit analog to digital converter. Another thing was that Code Composer crashed often. If I lost, if there was like a surge in power from connecting the Bluetooth module or anything, I would have to start over. If I changed code while I was debugging, I would lose the code, and there's just a lot of issues with Code Composer. Texas Instruments updated their hardware and software, mostly the software. It used to be branded as Oscilloscope, and they changed the brand to TivaWare. And TivaWare is a more simplified and like generic brand for Texas Instruments, and so there was a lot of code changes in that. The hardware really didn't affect me, the changes that were made there. And so when I had issues with my laptop, I had to reinstall and I had to change a lot of the code, which set me back. I tested 2 Bluetooth modules. They were both sort of easy after UART was working to connect. The JYMCU has default settings that make it pretty simple to send. The other, as I showed before, has initialization, which sets everything. So in the current status of the project, the SSI interface with programmable gain amplifier is currently working. So I have my 16 discrete gains that I can use on the incoming signal. My timing and data and all the connections to the programmable gain amplifiers are the same, so they can only currently have the same value of gain on both of them, which is something that I need to change. And external sampling of the analog to digital converter. Initially, it's used mostly for sampling the temperature of the microcontroller. And my interrupt is also working for receiving signals over Bluetooth. And my code for sending data over Bluetooth is also functioning. I'm sending 1,000 bytes of data, and then have the terminating character which repeats. Bluetooth is also working, and I have an interrupt for the hardware buttons, which are used to change the channels. It's just like a binary on and off for each channel. And my LEDs are working also. So I didn't get it the way that I'd like to by the end of senior design. I wanted to get daisy chaining working on the 2 programmable gain amplifiers, but there was an issue with channel select returning to high when it should stay low over the 32 bits that I was sending out. So I'd have to use a different way to signal my channel select, probably through GPIO. And I never got a MATLAB client to work. It was something I was trying to finish up right at the end so that you can actually tell like it's an oscilloscope. And battery power management is important because I want to use this as a mobile device. And because I didn't have a MATLAB client for it, I wasn't able to test the accuracy of the signal. And I also needed to have more polish on things like switching the LEDs to be interrupt-based. So I have engineering constraints. Health and safety. First, this type of oscilloscope is good because you can use it to remotely monitor a signal. You could like put it underneath the hood of a car and monitor a signal. And if it's like a hot environment or something, you can monitor it. Or just like falling objects or anything like that. Manufacturability, it's cheap and simple compared to a digital storage oscilloscope because there's no screen, and the case itself is much simpler. And for sustainability, a digital oscilloscope replacing CRTs, which have leaded glass, which are very expensive to recycle now because they're not producing CRTs anymore. And finally, economic constraint is I'm using low-cost parts for this project. So the market market for this is digital storage oscilloscopes that are generally cheap, and there's very few that connect to like Android or iPad. These two up here are almost $300, and they only go to 6 megasamples per second, which compared to other oscilloscopes that go much higher for much cheaper, the only difference is that they work with those two mobile operating systems. And then these two here are cheaper ones, and this is pretty much like entry level for like handheld digital storage oscilloscopes. Here's some pictures of what those are. This was the kit. That's $60 and it's the cheapest one. So you have to put your own oscilloscope together in order to have it. These three are all 1 megasample per second, which is the same that my board can do. And that one up in the corner is the Android one that goes at 6 megasamples per second. So the cost of my Bluetooth digital oscilloscope was around $22. That's not including all the extra things, but it shows that to add like plastic injection molding and things like that for like a very simple case that also a battery,